I'm going to talk a little bit about some work that's been going on over the past few years. Of course, so I don't forget to thank my sponsors. I'm Reed Maxwell. I'm with the Colorado School of Mines. And this work is very generously funded by the US Department of Energy through what we call the Ideas Productivity Project. So, as no secret, as Jenny really nicely wow, my talk's not even done and you're popping the champagne already. I appreciate it. So as Jenny really nicely introduced, we have really large-scale problems, right? Some great figures from Petra Dahl's work, looking at Petra Dahl, I like the pronunciations of everything, of Petra Dahl's work, looking at large-scale water use and depletion. And we have the same thing with land cover change. And we might say, well, what about observations? How can we observe this system? And we have huge scale discrepancies in terms of observation. And I think this is one of our biggest scientific challenges and also one of the most exciting scientific challenges. I love this example because here we have pumping wells, right, with about 1 meter support volume. And here we have GRACE with something like GRACE version 1.0 with something like 300 kilometer on a side pixels. So we have so many orders of magnitude discrepancy. And we have a call for models to become more mechanistic. And this is a great paper that Martin Clark contributed to the 50th anniversary WRR issue. And we have this call to make our models less empirical, more mechanistic. And if we start to think about these scale discrepancies, these big questions, there's really a lot more questions than we have answers. And we see that there's a lot of overlap, but there's also some real big gaps in terms of our scale coverage. So individual crops, our irrigation decisions are made down here. Our farmers are making decisions in this region. We jump out to sort of the national planning side or our large aquifer side, and we see that we've got some really noticeable gaps in these scales. And so we might say, well, let's use modeling to bridge this gap, right? It's a very natural approach. The question is, what kind of model and what sort of model is best in this? There's a lot of different approaches that have been applied to modeling these complex systems, particularly at large scale, and it's not really clear which is best. Now we have what we could argue are two physically based models. We have traditional land surface or hydrologic models. We have our grid or nodal, might call this integrated model, but you might even put ModFlow and other models that are just groundwater only in this category. And all of these models start with the same basic processes, same basic assumptions, but then the assumptions that are made to, say, isolate each watershed or isolate each pixel, neglecting lateral flow for vertical exchanges, we're not really sure how these play out at large scale. Versus we know, if we integrate all the physics and we include all these connections, we know this is a very complex nonlinear system. And these are really hard problems to solve. So computational hydrology is a great approach for this. We can solve these PDEs. We can throw really robust solution techniques at them. But we end up with these really hard problems to solve, particularly if we want to start to directly address these scale discrepancies. So we're starting to, as a community, try to understand if there is a penalty that we pay for model simplification. And so we can run models against each other, standard problems, benchmark problems, if you will. And this is some work that came out last year, Stefan and about 18 other of us modelers. And for a particular problem, what we start to see, this green curve, we really get a divergence between our simplified models and their solution and our integrated models. And we see that our integrated models tend to group together other models that make other, maybe an iterative versus globally implicit, type approximations start to drift off. And so we start to see, for some kinds of problems, real differences. Now the question is, do these play out in the real system? And that's a big part of what my talk is going to be about. So in my group, as you've already heard yesterday from my plug, we use and develop the integrated hydrologic model PARFlow. And I call this computational hydrology, sort of borrowing from computational fluid mechanics. We solve 3D Richards equation everywhere. We have fully integrated surface water versus the shallow water equations, either kinematic or diffusive. Now, PARFlow is built to be parallel from the ground up. And we have our own land surface model, descendant of the original CLM common land model, which is what the community land model is descended from, and ours as well, which has full land energy balance, snow dynamics. We drive this model, drive these simulations by observed meteorology. And this coupling allows us to really start to look at and diagnose interactions and connections. And so in my research, what I really push are these controlled numerical experiments. And the idea is that we take a system that's got lots of complexity, but is in fact a set of equations that matches a lot of our conceptual models of how the system works. And so we can solve these sets of equations to test our conceptual model, to test our understanding of the system. And I really like to take a perturbation, keep everything else constant, run these controlled numerical experiments, and then perturb the system, and then see what happens in terms of connections. See if A is still connected to B. So the topic I'm going to focus on today are how high-resolution, large-scale, integrated hydrologic simulations can tell us about how much water trees and plants transpire. So ET, I know we've been pretty subsurface focused, but evapotranspiration is the largest terrestrial water flux, larger than more water moves between the land surface and canopy and the atmosphere than flows in rivers and streams. And we have some recent estimates, and there's actually a flurry of literature on this now, that is kind of honing our transpiration versus total ET. So transpiration, the water that trees use inadvertently as they photosynthesize, it's about 62%. So largest terrestrial flux, more than half of it is transpiration. And what we're seeing is that our models really struggle to represent this. This is a picture, this is an image, this is a graph from Schlesinger and Jasheko, came out a couple years ago. And what they did was they plotted a number of stand scale estimates of transpiration partitioning, some isotopically based, and this is actually from Jasheko 2013, which has been corrected a couple times, once by Miriam Kenders, and then there's been some revised estimates. So this is a little bit high. It's really closer to like 62%. And then we have sort of a suite of standard land surface models over here. And we see this pretty big difference between our kind of 60-ish%, what we see in terms of our individual stand level estimates, and our models. And so I was really curious about if we could start to use models to bridge these scale discrepancies, right? These are large-scale hydrologic models at coarse resolution. These are stand-scale estimates. Is there something to bridging these scales? And so high-resolution hydrologic models have been this valuable tool for this. And so the idea was that we can start to run these high-resolution simulations at large scale in order to start to bridge these scales. And why do we think that this might be important? Well, I maintain that groundwater's role in the hydrologic cycle is really underappreciated. We have a range of paths and scales in groundwater. Water moves really slowly, via Darcy's law, of course, but our pressure can move quite quickly in the system. We can have very fast pressure response in the system. And this creates a system that's been well documented to respond over a really wide range of scales. And topographic and land surface processes have this really strong influence. And there's two really nice studies at completely different scales. This is Roy Haggerty's work from early 2000s, and this is Jim's Nature paper from 2000, both of which show that we're getting very complex behavior and that our traditional exponential type models don't represent these more fractal or more heavy-tailed type behaviors that we see from groundwater. So this is not a new idea. There's a whole community now, just as we have a community intercomparing hydrologic models. We have a community now pushing forward the so-called hyper-resolution model. This is Eric's term from his position paper. We have Mark's paper, which came out a couple of years ago. Hyper-resolution, everywhere and locally relevant. The idea that we have this large extent, but that we can still bridge these local scales. And so if we want to do this, if we want to say, oh, let's try this out, we could do a couple different things. We could reduce spatial resolution, which has been done. We could simplify physics and run at high resolution, which is a little bit what I'll show. And then we can hit things with a big sledgehammer. And I'm not particularly good at math, so my sledgehammers are pretty simple. My sledgehammer is a big computer. Let's take a model that scales well. Let's do sort of the very simple thing of run it at very high resolution and just throw a really big sledgehammer or a supercomputer at it. So that's what we did. And this is work that spans a couple of different papers. This is perfect time for me to highlight the contributions of others on this project, notably Laura Condon, who's assistant professor at hydrology and water resources at University of Arizona and has been really key to this work. And then Stefan Collette, who is at Bonn University and at the Research Center in Jülich, who's also been very engaged in this and is doing this over continental Europe now as well. So we built this proof of concept, didn't even really know if it was going to run, 6.3 million square kilometer domain covering much of the CONUS. It's 1 kilometer lateral resolution, which you could argue is either very high at this scale or incredibly low resolution at finer scales. We use variable resolution over the vertical. It's actually not that huge. It's about 32 million unknowns. And we built it to cover the Mississippi and Colorado watersheds. And it's fully integrated, 3D Richards equation, shallow water equations, land surface processes. So I'm happy to talk a lot more about data. I'm going to talk a little bit about input data here, but this is a very long discussion that I'm happy to dive into. What we wanted to do was use off-the-shelf data sets. Obviously, these data sets have lots of imperfections, and we didn't really want to try to massage or hide these data sets. Really, the idea was not to say, we don't have adequate data sets, so we can't do this. We wanted to push forward and say, yes, we know the data sets are inadequate. We know that there's issues. We're working with the best that we've got, but we're also showing that this is possible to also accelerate or push forward these advancements of these data sets. So we used standard land cover, Statsko Surgo soil, and then we used the hydrosheds, we used the now Glimpse, Gleason et al. This was an older version, but same idea, subsurface properties. And this represents, of course, steady state. Well, this actually represents pre-development conditions, and this is what I'm going to show you is a fully transient simulation. So what do you get? What do we see? So when we run these simulations, this is water table depth. This is daily averaged. What we see are actually a lot of really interesting things. So of course, it's really easy to focus in on shallower regions where we have water table that's responding very quickly to rainfall events. But if you can let your ADD go for a second and you focus in on the mountains, you can actually see a pretty clear seasonal cycle from snowmelt.
What year is this?
I'll show you in just 2 slides. We can also look at latent heat flux. Latent heat flux is completely dependent at one level on average daily radiation. And it's like almost hyperspeed, right? And this is just the cloud cover. bouncing back and forth. But again, then you can see some really clear seasonal patterns, and you start to see topography pop out in our latent heat flux values. So now to answer Jeff's question, this transient simulation was just a proof of concept. This is hourly forcing, again, off-the-shelf product. This is NLDAS2, which has warts and all, has lots of issues. We chose water year 85, so October 84 to September 85. We did this because this is actually the most average precip and temperature year on record over the CONUS. And the joke that we use all the time is it's always raining somewhere over the continental US. And so it's really hard to say, well, what's average? But there's really only about one average year in the NLDAS record. There may be more that we never observed. This took about 450,000 core hours on the Yellowstone supercomputer, which is on 2,000 processors was about a week of wall clock time, which is big, but it's not crazy. What is sort of crazy is that this is 12 terabytes of model output and 3 terabytes of input per year. This is 1.3 trillion variables, hourly, over the water year. And verifying this is a pretty big challenge. And we did the best we could. So we pulled together a validation data set of about 1.2 million comparison points. So snow, streamflow, and groundwater wells. I'm just going to touch on this. Again, input data could be a whole discussion, and validation, or what I like to say is comparison to observations, is a whole other discussion. What's really important about this is that we didn't want to say the model was right or the model was wrong. Because depending on how you look at this, you could say the model's right, the model's wrong. And that's not really productive. That's not really helpful. What we really wanted to do was say, OK, we know the model's going to be wrong. We know the model's going to have bias. What are our sources of bias in the simulation? And this is a table from a 10,000-word SI that nobody will, with 21 figures that nobody will read, but it's all here. Meteorological forcing, our scenarios and water management, our topography, our grid resolution, model input parameters, right? Model physics is also part of this. All of these things, right? Errors in this whole system could have impacts on our outputs. And we really wanted to try to get at understanding where these sources of bias lie. And so what we did was something a little bit different. So this is our Streamflow Comparison. So these are our 3,000 gauging stations compared between model and observation. And we broke them into an XY axis. So we have Spearman's Rho, which is indicative of timing and streamflow shape. And we have our volume. So we have volume bias and timing bias. Green is good, right? So we have low bias in our volume. We have good timing. That's about half the wells, or half the streamflow observations. Purple, which is about 30%, is the right volume of water, but not the right timing. Blue is right timing, but not the right volume. And red, which is about 10%, is wrong timing, wrong volume. Now we can look at this on a map to try to understand, are there systematic or regional biases to where we're doing? We do really well in the more humid East Coast. Model performs pretty well there. We actually see a lot of flips between green and purple as we move through some of our really big water projects in the West. Right? We don't have any impoundments in this model. So we have the right volume and we have the right timing until we get to a big water project, we get to a big dam, and then we're wrong. It's really interesting to look at the Midwest and the Ogallala Aquifer because we have a lot of red. And a lot of these are actually over-prediction. And I actually think this is groundwater depletion. I think this is the map of groundwater depletion, which is also not in our model. So we can start to understand not just if the model is right or if the model is wrong, but what are our sources of bias in this simulation? And how do we start to understand, do we have the model physics right, but the forcing's wrong? Do we have the forcing right but the wrong model physics? Is it the wrong model input parameters? There's so many pieces to this. Okay, so what does this have to do about ET partitioning? Right, remember that was my motivation? It turns out you have to actually believe the model before you believe any of these sorts of outputs from it. And so we always get into this segue of how well does the model do, how well does the model perform. And if you believe that, maybe you don't, we can now try to understand how the model represents scaling. And what this figure is, these are histograms, PDFs of our simulated T over ET partitioning, broken into basically similar categories to what we saw in the Schlesinger and Jascheko figure earlier. So we have mixed forests, we have deciduous forests, evergreen forests, and then we can compare them not only to our stand scale estimates, so this is just the data from that paper replotted, and now we include our two isotopic global estimates. And this is, one is Stephen Good, and the other is Jascheko as corrected by Kenders et al. So what we see is that we get a pretty good reconciliation between our individual stand scale estimates, our overall transpiration partitioning, and models. And so one of the questions is why? What's the process? Because we're up at about 61, 62% average, which means it looks like we're about in the right spot. And so we really wanted to try and diagnose a couple different things. And the easiest thing we can do is we can make our model look like a simple model. We can turn off lateral flow. Just turn off lateral flow. We now have column physics, and this runs exactly like any other land surface model. This is basically running like CLM. And what did we find? We've reran everything else exactly the same, turn off lateral flow. And what we get is systematically we get about 15, 16%, sometimes 20%, depending on the land cover type, drop in our T over ET partitioning ratio, which is really interesting. So now we turn off lateral flow and we jump over to look a lot more like the land surface models. So why lateral flow? What's the important piece? So our hypothesis is, and again, we can use these sort of large-scale diagnoses from models, we can plot latent heat flux. This is annually averaged. Each dot is a model pixel. We have them colored by soil type. And we see characteristic relationships, this is log water table depth, between latent heat flux and water table depth. We've shown this before. People have observed this. This is not new. We can also look at bare soil evaporation and our transpiration. So we have three main components. We have canopy interception that gets re-evaporated. We have water that is on the bare soil and evaporates from the soil. And then we have water that the trees transpire. And so one is just interception, re-evaporation. There's not really any surface hydrology going on in that. So we really wanted to look at T over E. So transpiration over bare soil evaporation, or these two components. And so what we see is that we see a pretty different relationship between transpiration than our bare soil evaporation. And when we look at this T over E ratio, we get this really interesting logistic curve. And so what we hypothesized, this is just our hypothesis in our conceptual model, is that we have deeper accessibility for deeper root systems that maintains transpiration under more water limited conditions or higher up the hill slope as we have it here. So we have trees, we have our bare soil evaporation, we have a hill slope, we have just a straight linear water table, which is super simplistic. One side, everybody's water limited, so everything's shut off. The bottom side, everybody's got plenty of water, nobody's water limited. But in the middle, we have these two different relationships for different water stress. One for plant water stress and one for bare soil. Bare soil is just the very thin top layer. So that's going to shut off more quickly. And that creates this T over E logistic relationship, which may explain, maybe this is right, maybe it's not, but it's our hypothesis based on our model simulations, that this discrepancy. Now, what's really interesting about this is this has a lot of implications for plant water use strategies. And I am really interested in trying to move this forward to understand how we understand how plants use water. Of course, here also, there's a lot of people doing this as well. Daniela just had a great paper published on seasonal rock moisture. I'm going to focus in on some work out of Roger Bales's group and the Southern Sierra CZO. Now, both these papers are in common because they both observe systems under the historic California drought. And what was really interesting, and to me, the most interesting piece of Roger's paper is that we see a crash in precipitation. We see a crash in stream flow. But they had an eddy flux tower going the entire time before, during, and after the drought. And ET barely moved. So what the heck? We had this historic low water input, yet ET basically didn't change. So can't talk about this without talking about my group. My group studies a range of topics. And one of the things that I like to do in my research is we like to go from these small scale point observations to fine resolution models all the way out to larger scale. So use models to sort of bridge these scales. And I'm going to focus in on a little bit of former master student, Kate Collins, who got really interested in these water use, plant water use questions, particularly funded to work in the Southern Sierra CZO. So the Southern Sierra CZO, she ran this very small watershed, Providence P300, and includes these different subwatersheds. And I think the takeaway is that it's this natural laboratory that happened to be active during one of the worst droughts on record. And so if we look at Kate's model simulations, these are her model simulations replotted like Roger's plot, we see that 2011, we have high precipitation, we have high runoff. 2014, we have really low precipitation, low runoff. And if we compare uncalibrated model, what we see between the model and the observations, we get pretty good agreement, but we also see the same characteristic behavior where transpiration, ET, doesn't decrease on average. Runoff and precipitation crash. And if we use a remote sensing product like MODIS, we get a really different answer. And so what we hypothesize, and these are different scales, but basically this is just showing the Bales et al., the Southern Sierra CZO group data. What we hypothesize is that we get this relationship, we get these same results for the same reasons that we see at large scale. And so now this is a replotting of those latent heat flux versus log water table depth, bare ground evap versus log water table depth, transpiration versus log water table depth, and then T over ET ratio, now colored for non-drought in blue and drought years. And what we see is actually transpiration doesn't decrease. And if we look at this spatially, what we see is this is in areas of convergent water table. And so basically we have convergent lateral flow and water table that's supporting plant water use throughout the drought. And so last piece of the whole puzzle, maybe, we'll see if this, how things play out, but I got really interested in how the model represents which water plants are actually using. And I have been doing Lagrangian particle tracking since the beginning of grad school. And so over Christmas break, I wrote a new code, which I'm calling EcoSlim. And what EcoSlim does is EcoSlim reads parflow and CLM output, and it dynamically puts in particles. So every time it rains, every time the snow melts, every event, it adds particles to the simulation. And then I actually borrowed from way back when we ran coarse resolution groundwater models, and we weren't able to delineate the capture zone of the well. We had these partially penetrating well random approaches to how much water got captured in the well capture zone and got removed. And so I actually reformulated that for ET. So we pull water out over the root zone based on ET. And this is all after another PhD student, Lindsay Barrett, who actually kind of came up with the idea of this. I sort of formalized this, wrote it in parallel. It actually runs really well. And this is in review and environmental, ecohydrology letters. So what does it do? So we can add, this is just a movie, right? This is our particle source. This is a mostly rain-dominated system. We have like little bands of snow coming in. And we can run and spin these systems up. And so we can run them for years and years and years, spin up the ages. There's age, there's source. All of these things are going on. It's completely transient, running at hourly time steps in this particular instance, fully driven by the observed meteorology. And so we can spin the system up. We can spin the age of the system up. We can run these systems to equilibrium. But then we can also look at, say, what our outflow looks like, and look at, say, groundwater contributions to stream flow. This is just the fraction of rain, snow, and pre-event groundwater, if you will, in our outflow. And then we could do the same thing with ET. And we can see really interesting things, like we see very little rain in this particular example showing up in our outflow. We have a snowmelt-dominated system, so we get mostly snow. But then we see that late summer, we get the snowmelt signal, but then as soon as it starts to rain, plants are just switching over. And we don't have any intelligent plants in this model. This is just hydrologic constraints. But our plants are effectively switching over and using the rain preferentially. And then when there's not much else available, they switch to groundwater. And so we can maybe start to unravel these systems through these different tools. So, conclusion slide right now. Look at that. Landed the plane right on time. So we see connections between hydrology, land energy fluxes, lateral flow is super important. And I think we really need to think about these simulations as numerical experiments that go in tandem with observations to get at these processes. Right? Do we see these same sorts of relationships? If we do, great, if we can observe them. If we don't, that's great too, because then we go back to our conceptual model and we say, there's a piece missing in our conceptual model that we need to think about, we need to consider. And in these big sort of grand challenge simulations, I think it's really important that we engage the community. Right? We have these now many years of these 12 terabyte per year simulations sitting. We don't really have a good way to serve these, to broadly share these with the community. And I see this whole large-scale modeling as a big process. And so we started out here. This is like the GMD paper. This is the science paper and Laura's Hess paper. And then we're adding pumping. We're extending the subsurface. We're improving model physics and other pieces, and eventually coupling to WRF hydro and sort of merging in with the idea behind national water model. And so we have a domain now that matches up with the national water model. We're running at higher resolution, and we sort of see this as a community computational tool moving forward.
How could you package the work that you do in such a way that it makes it, is accessible for communities?
That's a question that we ended up writing a research proposal about because it became so sort of complicated. And I'll give you the quick thumbnail of it. It turns out in talking to the community that there's about 3 different levels of user group. There are a lot of users that just say, I want an easy way to cut and paste from the data, and I want it served, and I want it, I want to be able to either just grab prepackaged or, some pretty easy way to interrogate the data myself. Then there's a group of the community that says, I want to keep everything the same, but, could you run it with a different year, or could you run it with a land cover disturbance, or could you, rerun the model, or empower them to rerun the model, but do just a slightly different thing. And then there's the users, like a lot of you in the short course, that are like, I want to learn how the model works and maybe adapt it to my own system, or maybe even say, oh, I've got a new physical idea about how this should work, and I want to put it in your model and test it at the continental scale or something like that. And that's a different branch, and there's different approaches for all three of these. It's really interesting, but it's actually proved a lot harder to serve the data than you'd think. And we've explored a bunch of different options, but they've not quite panned out super easily.
I have some difficulties about your scale parameters in the large scale model.
Okay.
If you take the average spacing,
Mm-hmm.
the average size of each slope all over the world,
Mm-hmm.
you know, on average, it's about 1 or 2 kilometers.
Mm-hmm.
Like that. So it means that in one grid pixel,
Mm-hmm.
you have a very small river
Mm-hmm.
with a fluid water fluid parallel to
Mhm.
the river and a groundwater fluid which is likely perpendicular to
Mhm.
the main stream. So how do you make the difference between surface flow and groundwater flow, and how you can define the Malin coefficient, for instance, at this scale, which is a very big scale compared to the scale of hydrology in general?
Fair point. So the question is basically 1 kilometer sounds like incredibly high resolution when it's 6.3 million square kilometers. But if we were to go instrument our hill slope and think about it as a 1 kilometer model, it would sort of be crazy. It would be so low resolution that it wouldn't make sense. And I think the answer is actually that it's sort of surprising that the model works. And it's sort of surprising that, and what it tells us about this is something about upscaling. Because topography is fractal, right? So you're never at high enough resolution to resolve the system. You're always cutting something off. And we don't have a closure. We don't have some scale-dependent closure that says, okay, this is, these are the processes we're missing either topographically or because of variation in land cover. And so you're absolutely right. We're only capturing processes that happen at the 1 kilometer scale and larger. But yet we actually end up capturing quite a lot of pretty detailed processes all the way down to mountain headwaters watersheds. And so I think what this tells us is that you're right. I mean, we don't address these small sort of subgrid heterogeneity pieces, but yet we still get a lot of fidelity out of these models, which I think implies that some of these processes are disappearing at larger scales. Now, I think implies is the right word, and I think that it depends on what your question is. If your question is the soil moisture or the water table depth going to compare to what I measure on my hill slope? Absolutely no way, right? Of course, it's not going to match. But if your question is at larger scale, or for plant water use, or for even moderate-sized basins, do we have the appropriate hydrologic response and even maybe the appropriate description of heterogeneity? Maybe it's not so bad. But I think that until we do this and until we push this forward, we're pushing forward in even higher resolution. We have 250-meter grids. All of this is feasible. We're pushing this forward. We can understand at what point do these processes emerge, these processes matter. Now, my own opinion is that we need some kind of a closure. We need some kind of a scale-dependent closure in hydrology. And I sort of run these models to put myself out of business. Sort of run these models to say, we run these high-resolution models. We learn something about how the system works so that we don't have to run these models. This is a big numerical experiment. And what can we learn from it? But yeah, your point is very well taken. And this was actually a very common argument with Mark's paper, the everywhere and locally relevant. The locally relevant part gets really hard if it's 1 kilometer and your hill slope's 100 meters.